Generation technologies, we've invested in a clean coal company called Cleantech, an oil and gas wellhead equipment company called MSP DrillX, a next generation lithium ion battery company called Mobius Power, and a power management semiconductor company that's targeted at the solid state lighting area in Exclara. So, over the next couple of slides, I'm just going to do quick vignettes on a couple of these sectors to give you a bit more of an overview. Again, to give these areas full treatment would require a separate session of their own, but I'll try to give a quick bird's eye view in any case. So in solar, on the top row, you can see some graphics that show the value chain for the standard crystalline silicon manufacturing process. And it starts with the raw material of polysilicon, which, depending on the type of process, you'll do your crystal growing and you'll pull ingots that get cut into wafers. Those wafers are processed into solar cells, which then get packaged into modules, and then finally get installed with all the wiring, inverters, and balance of systems on your rooftop. And so there are a lot of different cost steps along the way, and depending on how vertically integrated the companies are, a number of companies changing hands with different products along the way. A lot of the innovation that we've seen has been trying to take parts of the value chain and making them much more efficient or cost effective. So starting all the way down to the left with the polysilicon process, as many of you who have done semiconductor work know, in the early days, solar was using semiconductor grade silicon. So they were trying to get the same supplies of silicon and making similar types of wafers, but making solar cells out of them. And for those of you who have done some research on the solar space, you'll know that you certainly don't need the amount of purity levels that you need in semiconductor grade production. And so folks have experimented with ways to use metallurgical grade or upgraded metallurgical grade silicon to produce solar cells with high enough efficiencies to be competitive. On the wafering side, there have been other techniques for how to do crystal growing, how to pull your ingots. Folks like Soleix are working on what's called the continuous Trikalski method, which can create ingots that are much more pure, have much better uniform resistivities, and result in solar cells that have higher efficiencies. And then different types of ribbon technologies, which instead of pulling ingots in the standard way, you're pulling the silicon material in a much thinner way to be able to create wafers in yet a different method. On the cell side, a lot of innovation has been done at the crystalline silicon level, where folks have done back contact cells like SunPower, which most of us should know in this room, sliver cells, which is thinking about how you cut wafers into much smaller pieces and then repackaging them in a way that allows for better light trapping techniques and higher efficiencies there and lower costs. And importantly, thin film is yet another way of manufacturing cells, which many folks have heard about. A number of different materials that have shown very good band gap absorption properties that have been used over the past 20 or 30 years, including amorphous silicon, cadmium telluride, SIGs, and CIS, which many of you have seen in the press. It's captured a lot of attention. There's also been folks who have been experimenting with dyes and organic materials to try to create lower efficiency cells, but ones that can be produced roll to roll and at very low cost. And then even newer materials like Styon, which are trying to innovate on that to create very optimal materials for PV. Concentrated PV, so taking cells and figuring out ways to concentrate light on them more effectively so that per cell, you're getting more efficiency per unit silicon that's in there. That's also been another area. And as we move to the right, module packaging has been another area of innovation, trying to figure out how to package these cells in a way so that you lose as little optical efficiency as you can or reduce the cost of the glass and all the other materials that go into packaging that. And then balance of systems, one of our panelists later was an investor in a company called Petra Solar, which is trying to figure out a way to, within a solar system installation, figure out how to balance your power management across so that you can get the most optimal balance across at any given point in time, so that if there are any shading effects or any other types of environmental conditions that make certain cells collect more energy than others, you can balance it out with the right type of technology. And last but not least, on the solar financing side, there have been a number of companies that have been innovating on ways to allow residences as well as commercial installations to be done with very little upfront cost and take advantage of tax arbitrage to be able to manage that effectively. And then kind of ancillary technologies, solar thermal is one that many folks probably have heard about, which is the act of converting heat that comes from the sun and the atmosphere into energy. Combined heat and power, different types of techniques to do heat exchanging within a given building so that you can recycle the heat and again convert into electricity. And then capital equipment plays where folks who are trying to do sell equipment to solar manufacturers for improved inspection and metrology techniques, other types of deposition type of equipment that can be faster and more efficient and so forth. So suffice it to say, solar has a considerable number of opportunities that are very relevant to folks in the Silicon Valley, especially those with semiconductor backgrounds. So smart grid is an area that has seen a lot of press lately. About no less than $5 billion of the stimulus package will be going into infrastructure around the smart grid. So what does that mean, and what are some of the opportunities that could potentially be useful for the group here? I apologize for the graph here. It's a bit small to be able to see, but we'll distribute this after the presentation. What this graph is depicting is a number of different parts of the grid that represent opportunities for entrepreneurs. So the circle at the top are consumer devices. The ones on the top right are communication devices. So every house has a meter, and there's been considerable efforts across a number of the utilities to make these meters smarter so that the utilities can get more real-time information about the amount of electricity usage that's being done at each building. And the communications devices will be the common infrastructure that will overlay that to allow these meters to talk to each other and ultimately talk back to the utility. Now, why is that an important concept? For those of you who have done any research on the utilities and the amount of information that they can get, for the last 30 or 40 or 50 years, the grid infrastructure has been a patchwork quilt of different devices that have been put into consumer homes at commercial installations with very little thought as to how you communicate and grab the information. The meter maid or the guy who kind of comes every week to read the meter on site, immediately comes to mind. And frankly, that hasn't changed nearly as much as it should have. And so the next generation of the grid is really going to be about smart devices that are able to communicate with each other to give the grid to give the utility real-time information about how much energy is being used at enterprises and at households so that they can do much better demand management and make crucial decisions on what happens when the amount of supply doesn't equal demand and you need to have brownouts. So how do I figure out where I need to pull electricity away from in order to support the overall system? So there's a lot of innovation that's being done there. On the bottom left, we have energy providers. In the middle is kind of a network control, and on the right we have distribution. So from the household to the actual utility, there's a significant amount of distribution infrastructure with a lot of the transformers that you'll see in each of your housing communities. The actual power lines that go to substations. That entire distribution infrastructure is also one area that is seeing a lot of innovation, especially on the software side, where utilities now are starting to invest more in software packages that allow them to understand what's happening at the transmission line level. And importantly, what happens when you add solar, wind, energy storage, a lot of these distributed sources of energy onto the grid. How do you control all of that, and how do you match supply to demand in an optimal fashion in your distribution network? So that's yet another problem that folks are tackling at the utility. So we've been talking about the demand management side, energy resource management, and then last but not least, at the bottom we have the actual assets that a utility manages. So again, utilities tend to have very little visibility on the state of their assets. And so transformer monitoring equipment, or power line fault detection equipment, or different types of software algorithms to analyze the demand profile across your entire distribution network and transmission network. So a lot of these types of technologies basically have one uniform goal, which is to help utilities better match supply to demand. And today, we're in the first inning of an extra inning game on trying to solve that problem. And there's significant